For the past several years, experts in science, technology, engineering, and mathematics have been working hard on NASA's Artemis 2 mission, the first time we'll fly to the moon in over half a century. Artemis 2 involves special collaboration with 4 other countries, including Germany. The German Aerospace Center is sending a shoebox-sized satellite, known as a Cubesat, to hitch a ride aboard a ring that attaches the crewed ship, the Orion spacecraft, to the Space Launch System. NASA says this CubeSat, named Tokalos, will, quote, collect measurements on the effects of the space environment on electrical components to inform technologies for lunar vehicles. In outer space, there's lots of quick and far-moving radiation, since most matter in space isn't very dense, like in the form of atoms without electrons. Technology up there doesn't have the helpful protection from radiation offered by the Earth's atmosphere and magnetic field. All stars radiate, and there remains everywhere a lot of radiation from the Big Bang, known as cosmic microwave background radiation. Cosmic rays, which travel almost the speed of light and whose sources we aren't all entirely sure about yet, also pose a challenge. But while significant amounts of radiation come here from outside our solar system, the biggest nearby radiating body that Tokalos is interested in is our own sun, which emits all kinds of radiation, even gamma rays. Rather than design electronics that just have to work under terrestrial conditions, these STEM experts have to consider factors special to outer space. Space radiation can interfere with measurements and corrupt memory, drain existing power and harm solar battery cells, damage electrical circuits and interfere with currents when charges from radiation are trapped by materials like silicon, and even cause failures of entire power systems. And this radiation isn't a static threat. It varies significantly over the course of 11-year sunspot cycles, and as its spacecraft gets deeper into space. Radiation can create problems that develop slowly or without obvious symptoms, so simply checking a component's functionality often isn't enough to see whether it'll stay reliably protected from radiation. Additionally, shielding can hardly be absolute. Effectiveness isn't linear but faces diminishing returns. That is, the effectiveness of a certain amount of shielding may depend on how much is already there. All these complexities make new research, like that done by Tokalos, very important. The German CubeSat aboard Artemis 2 is a great example of how people in STEM fields are accomplishing amazing things, and NSTEM works to empower that expertise in future generations who will bring us safely to the moon and beyond. Contribute to this mission by starting a local NSTEM chapter or becoming an individual global member today.